Hey guys, welcome to my lecture part 2 on image acquisition. So in this video, I'm going to be talking about sampling and quantization. And in the previous video, I did talk about how eye is a natural acquisition tool of your body. So in this video, we would be seeing how a computer actually stores an image, what representation, etc. in this video. So let us get started. In our computer, we generally have a limitation as in the number of colors that you would like to represent, the intensity levels, etc. Since we do not have infinite memory in our computer, we have to quantize it and sample it to actually get a digitalized input. So but the main acquisition device would just be like a CMOS. So you have like a filter over here. This is just one cell, okay? So you have energy, that's your light falling onto this filter. Then there's some sensing material which actually converts these light energy to some form of digitalized input, like a voltage or a waveform. And then you have some power coming in, and this is just one cell, right? So an image can be represented either as an array of these cells. So these arrays of cells are known as a array, and also you can have a matrix. So you have the matrix representation of a cell, or you also have the line sensor. So this is basically your line sensor, and this is the matrix of the array sensor. So there are two ways to actually represent in your images in this form. So this is the basic unit. You have a line sensor, and then you have an array sensor. So basically images are formed based on some linear motion that's either in your, so if you want a 2D image, you will have a coordinate plane, that's your x-axis and the y-axis, and you would require there would be a sense of movement in the x direction and y direction to give you a 2D image. So for a 3D image, you would have 3 coordinate planes, and the sensor, or there should be some movement in x, y as well as z direction. So this is how images are actually constructed, and you would see that over here this could be some like a sensor, line sensor or something. This is one linear motion this side, the sensor strip moving this side. This would result in a 2D image. For 3D image, you can have a linear motion. This is your sensor ring, so you can also see this is your sensor ring. So this is like if you've seen the CAT or the X-rays, etc., the MRI scans, they want a 3D dimension of your entire body. So these kind of computed astronomy, tomography, etc., are require 3D things. So you have one linear motion this side, that's your patient, that will be going inside this. Then this would be rotating once, and this along would be rotating once. So the entire motion, this is like an entire 3 motions result in a 3D image. So you generally, how these images are constructed is through cross-sectional images. So you have the first cross-sectional image, and then another cross-sectional image of the body laid upon this the previous cross-sectional image, and you get those 3D arts kind of stuff. So this is entirely how the computer actually pictures up your thing. So like I said, your array, let's say in the previous thing I have showed you the line sensor. So how exactly this line sensor works is shown over here. So if you see an image basically is represented in the form of a matrix. I will go into this depth in later, but for now just assume that the matrix is a representation of an image. Each pixel over here has a certain intensity, which I will be explaining to you. So this is your array line like sensor. So every how does it actually denote the image would be like this. So you have an horizontal sensor, there'll be a vertical shift. So this is the first movement. So the CBA comes to the horizontal center, and then you do this is a vertical shift, and then you have a horizontal shift. That means these intensity values get shifted over here, and the output comes over here. So that is how you actually do a 2D image in a line sensor. All right. So but the first thing comes, the first limitation of your computer is that you have discretized images, right? So you when I say digitalized images or discretized image, it's just an approximation of the real image. And what I say about that is, let's say this is your scene element, this is some object which is placed under an illumination or a light source, and when the light hits here and it reflects, if your eye was present over here, then your eye would actually sense this image, interpret this image, and send it to the brain, and the brain would actually interpret what this image is, and then tell you what the image, you will actually see this image in your head. But in the terms of computer, what happens is that you will have an image sensing system over here, that's your CMOS, line array, etc. Some photoresistor kind of elements which would actually have a reaction towards light and produce a electrical signal. Now this signal then goes to your CPU or some internal processing unit, image processing hardware, and the software is required, and it would try to represent this entire image in the form of some discretized form of image that's in the matrix, right? So you would see that this image that is over here, this image looks so nice over here, but you can see it's a little distorted over here, because this is again comes as a limitation of the computer. Your computer does not know so many intensities, so it will try to approximate this particular pixel value to some value that it knows. So this entire process of converting this image, this scenic image, to a digitalized image is known as digitalization. This happens through sampling and quantization, which I will mention to you now. So before actually stepping into it, there are some conventions in image processing. Your entire image is represented in the form of a matrix with 0, 0, that's the first coordinate starting from the top left corner of your image, and the y-axis goes this side, the x-axis goes this side, and you have a point over here called x0, y0. Just a representation. You may have different representation, but this is the convention that I would be following in my lectures. So what for a 3D output? So this would be your 3D, a 3D image has an x, y, and an fx, that's your z-axis. So if you take it in the 2D plane, you look from the top. So you will have the bird eye view of this. It will look like this. And the origin is over here. The y-axis is side and the x-axis this side. And then, represent each value. So each small pixel with the intensity corresponding to that particular location. So this small point over here would have a 0 because it's the darkest and it's assumed to be black. So that's the approximation that you can get. So this is the digitalized form of things. So approximation of the intensity values to this is some limitations that arises due to the computer. That is why you have these kind of measures to say how good the quality of the image is, like what is your intensity value, or how many dots per inch. These are some representational terms, because let's say in the previous image or this image, if the boxes were even smaller, then I think you would have got a good approximation of this image. So the more dots per inch results in a better quality of image. So these are certain terminologies that you would actually come across in image processing, and I will also discuss it in this course. So like I've mentioned to you this. So you have a 2D image, you have the light source, this is the camera. The camera only captures the first, like a 2D form of image. So you can see you have, this is the world, this is your lens, your camera lens. It gets some image, it digitalizes the image, as I've shown, some sort of approximation that has been done, and then you get the digital image, which is considered to be an approximation of the image that is formed in the real life. And who does all of this, where it's all stored? It's all by the CMOS sensor. So yeah, like I've said over here in this slide, I did say you about how this image that is formed over here is in terms of the illumination and the reflection with some noise. All right, so the illumination is the amount of light that is present in that particular time frame. Reflection is this particular light that is being reflected from the scene image. Okay, so it is generally the amount of light that can actually come across could be anywhere between 0 and infinity. So you do not have like a negative light source as of now. So it's always like, the darkest color is considered to be 0, and then infinite means that it's the brightest one. It's an assumption. So it's illumination source. And then the reflection is the amount of light reflected from the amount of light that is observed. All right. So that is always between 0 and 1. That's like a quantity that says that if 1 means all the light is reflected, it's a completely shiny object that reflects all the light that is absorbed, and 0 means it's like a black hole kind of stuff that absorbs all the light. And since we are in a real world, you always have noise. That's an additional factor which distorts and gives some form of disruption in your image. So this is what I'm saying. So now, like I'm saying, so f of x, as I said, intensity, it's proportional to the energy radiated by the physical source, right? So this is the intensity of the light. So you perceive objects around you as a form of intensity. Then you have an illumination. It is also the amount of source of illumination incident on that scene that's being viewed. Like I just said, the amount of light that the object can observe, the world can observe, or the object that's present in the scene can observe. Reflectance is the amount of light that of illumination. So this is of illumination. So the amount of light that the object has taken in, how much can it reflect back? So it's always between 0 and 1, and the noise is like the various measurement of the results. So in general terms, you always have an intensity scale of L-min and L-max, okay? So this is like the intensity. L-min is the minimum intensity and L-max is the maximum intensity. So it's also known as the grayscale of the image. So basically your life is not just black and white, you have all shades of gray. So this is one form of represented. It's a grayscale image where it's very helpful to convert your images to grayscale, because that's like one of the key concepts of image processing. Makes your life so much more simpler than all the various colors that you actually have in world. So just keep it, white, black and gray. So the intensities always range from L-min to L-max. Generally L-max is considered to be 1 and L-min is considered to be black, that's 0. But in we do not like negative numbers, so it's just a common practice to shift this L-min and L-max to 0 to L-1. So like I said, 0 means black and L-1 means white. I will also come back to this in the next chapter. This is an introduction, so just take it light. So yeah, now I come to the most important point of this lecture, which is sampling and quantization. Like I said, the computer does not have a kind of superpower that can store up all information of the images. Images can go to the minute details, like how an artist paints, or it can just be us painting, which we just ignore all the details and you just paint the overall picture of it. So images can be detailed as well as non-detailed, but our computer can choose what it wants. It can only take certain aspects of the images that it feels is deemed necessary and store only those kind of images. Later, when you want to get back the images, you can always do an image reconstruction, but as of now the computer only knows that it does not have that much of capacity to store all the forms. So if it is a continuous signal, you would definitely have between this point and this point there are infinite intensities of voltages present, and the computer cannot store that much. So the only result that comes up is sampling the time. So in this, you sample the time. You just take only those points of time where you actually want to get the particular intensity value, and then just store that. So that is what is converting like an analog signal to a digital signal. You take in only those points that you find necessary and you just store those values. So again, it's the more the number of sample points that you take in, the more detailed your image becomes, and it's more close to the analog signal. So the main difference between sampling and quantization is explained in this slide. So I'll be very clear. Sampling is basically taking it from the input form of things. So choosing which points you want in this range. That's your time or whatever be that thing. So at this particular range, that's your horizontal axis, whatever values that you get, whatever values you let's say you want to take it from the second point or the third point or the fourth point or the fifth point, those are known as sampling. Quantization is through the amplitude. All right. So sampling is through the time frame or the horizontal axis, and quantization is the amplitude. That is, let's say this value is an approximation of this entire. So this is a particular range that you have. Alright, so this particular range, any value that falls in this range, suppose you have chosen this sampling point and it maps to this particular quantization value. So even if you had like this sampling point, it still maps to somewhere over here, this particular, the upper limit, but it still maps to this particular range of value. So that is what is known as quantization. So if you have seen in sampling, you just take in points and you get the amplitude value. But after that, you need to quantize it so that you have, you get the intensity value at that particular. It's an approximation of the intensity values that you can get through. So that is basically quantization and sampling. So the video has gone a bit too long, so I'll stop it here, and in the next video I will try to explain more about how this actually affects the quality of your image. Thank you so much, and hope you like, subscribe and share this video.